We spent a lot of time celebrating the huge scientific breakthroughs, right? The Nobel Prizes, the discoveries that completely reshaped our world.
Absolutely.
But we almost never talk about the cost, the actual price tag of that knowledge.
Right.
And sometimes that price wasn't just in funding or years of research. It was paid in health
Hmm.
or in the very lives of the people on the front lines.
It really is the hidden cost of discovery, and that's why this deep dive is so important, because when you look at the sources, you see this pattern. You see all these scientists, these researchers who paid this immense personal price
But their lives.
with their lives or their health because they were working with things that were just far more dangerous than anyone could have possibly realized at the time.
So our mission today is to really unpack these stories, not just to, chronicle a series of tragedies, but to understand the legacy.
Exactly.
Because these pioneers didn't just discover new phenomena. They also, tragically, were the ones who illuminated the profound dangers that came with them.
And that's the core insight here. It's almost cyclical. The biggest breakthroughs in physics, in chemistry, they almost always came before the safety framework existed.
There was no rule book.
None at all. No one had any institutional knowledge of what long-term radiation exposure did or what X-rays could do or these, ultra-toxic compounds. Their tragic outcomes are what directly led to the modern safety protocols that protect literally every researcher working today.
Okay, so let's start at the beginning of that journey with the scientists who really defined that slow tragedy, the pioneers of what we call the age of radium.
Yeah, and when we talk about that kind of slow, cumulative damage from radiation, you can't not talk about the Curies. The name is just synonymous with both the genius and the sacrifice.
Right. Marie Curie. She discovered polonium, radium, basically established the entire field of radioactivity.
She was, in a very real way, handling fire before anyone even knew what a burn was.
And the irony is just, it's devastating. She died from her work. Aplastic anemia. For anyone who might not know, what exactly is that in this context?
So aplastic anemia is a condition where your body just done. It stops producing enough new blood cells. And the reason radiation is so lethal over the long term is that it specifically attacks and destroys rapidly dividing cells.
Like in your bone marrow.
Exactly, the very place where blood is made. So her death wasn't, a sudden event. It was a slow, systemic failure of her body's most basic systems, all from that prolonged, unprotected exposure.
And when you read about her working habits, it's mind-boggling how little they understood.
It really is.
The sources point out she would carry vials of highly radioactive radium in her pockets. Just in her dress pockets.
She did, and she stored them in her desk drawers because they gave off this beautiful, sort of ethereal blue-green glow. She saw them as treasures, not as, invisible assassins.
That casualness is almost impossible to imagine now. But here's the part that really gets me.
The notebooks.
The notebooks. They date back to the 1890s, and they are still, today, so contaminated, so radioactive, that you can't handle them without full protective gear. They have to be kept in lead-lined boxes.
A century later, that lingering poison is like a physical monument to what she went through. It just shows you how deeply this material was woven into their actual lives.
And it wasn't just her. The sacrifice extended through her own family.
It did. Her daughter, Irene Joliot-Curie, carried on the work. She even won a Nobel Prize in chemistry in 1935 for creating artificial radioactivity.
But the family history repeated itself.
It did. Just like her mother, Irene died of leukemia, another fatal blood cancer that was, without a doubt, the result of decades of radiation exposure. It was a generational toll.
And it's so important to remember, it wasn't just the famous names, the Nobel laureates. It was the whole team, the people in the labs every single day.
Oh, absolutely. You have to think about people like Harriet Brooks. She's considered Canada's first female nuclear physicist. She worked with Ernest Rutherford. She worked with the Curies in Paris.
She died young.
Very young, only 56. The official diagnosis was a blood disease, but given her work and her proximity to these high-intensity sources, it was almost certainly a radiation-induced cancer.
And then there was Elizabeth Aschheim, one of Marie Curie's lab assistants.
Right. Our sources show her job involved handling those intense radium sources every single day. It was just part of her routine. And she died young of leukemia. Hers was one of the earliest documented cases of what they called radium poisoning that pointed directly to an occupational hazard.
These people were, they were the canaries in the coal mine.
That is the perfect way to put it. They were the first ones to demonstrate that just being near these things day in and day out was a death sentence. The data from their tragic deaths was what helped establish the very first safety limits.
So that history of slow, cumulative damage is terrifying enough. But radiation wasn't just in solid form, and the lack of understanding wasn't limited to radium. The scientific world was exploring all sorts of new, invisible forces.
Exactly. And that takes us from the slow burn of radium to the invisible beams of X-rays. And this brings us to Clarence Madison Daly.
Thomas Edison's assistant.
That's right, at the very dawn of the 20th century.
Edison was so excited about X-rays when they were first discovered. But Daly, he has this really tragic distinction of being the first person known to have died from X-ray exposure way back in 1904. What happened? How did it get so bad?
Well, the problem was their method. They were trying to improve the X-ray tubes, make them more powerful, but the only way they knew how to test the beam's strength was for Daly to put his own hands directly in the beam.
For hours.
For hours at a time, day after day, while they fiddled with the equipment. There were no dose limits, no lead shields, nothing. No one understood what it was doing to his cells.
That is just horrifying. Just holding your hand in an invisible beam of destruction.
And the consequences were grotesque. He developed these agonizing radiation burns on his hands, which very quickly turned into aggressive cancers that spread.
They tried to save him.
They tried everything. Numerous surgeries, even amputating both of his arms, but it was too late. His death was such a stark and physical warning that Edison himself was just deeply disturbed. He completely abandoned all X-ray research after that, said the beams were too dangerous to play with.
So we got the slow-acting solids like radium, the direct danger from X-ray beams. What about the air itself, the things that were just floating around the lab?
That's a critical point, the danger in the air they were breathing. The sources talk about the deaths of early radon workers, people like Sabine Govertz and Daniel Hegge and other students and technicians.
And radon is the gas that comes from the decay of radium and thorium.
Precisely. So these researchers weren't just touching the source material, they were measuring the emanations, the actual radioactive gas being released into the air, and they were doing it in these small, poorly ventilated rooms.
So they were inhaling it.
They were inhaling it day after day. They died prematurely from lung cancers and other illnesses that were directly linked to breathing that gas. These cases were foundational because they proved the danger wasn't just in touching something, but in breathing the air around it. That led directly to the first ventilation standards for labs.
Okay, so if the age of radium was this slow, decade-long burn, the dawn of the atomic age, especially during and right after the Manhattan Project, that represents a shift to something else entirely.
That's a huge shift.
We're moving from years of exposure to lethal doses being absorbed in seconds. Immediate catastrophic radiation death.
It's a profoundly chilling transition. We're now talking about critical mass, about uncontrolled nuclear reactions, and to do that, you have to talk about the accidents with the object that became known as the Demon Core.
A 9-pound sphere of plutonium.
Yeah.
And it killed 2 different scientists in 2 separate accidents, just a year apart. First was Harry Daghlian in 1945.
Right. Daghlian was doing what they called a tickling the dragon's tail experiment, bringing the core just to the edge of criticality.
And how was he doing that?
By hand. He was stacking tungsten carbide bricks around the core to act as neutron reflectors. And he accidentally dropped one of the bricks directly onto the sphere.
And that was enough.
Instantly. The core went supercritical. It flashed blue and bathed him in a massive burst of neutron radiation. He survived for 25 days, but it was a horrifying, drawn-out death from acute radiation syndrome.
And then, just a year later, 1946, the same core, this time Louis Slotin.
Yes, and this accident really highlights how reckless the safety measures were, even after what happened to Daghlian.
What was he doing?
He was demonstrating the same risky experiment to colleagues. He was using 2 halves of a beryllium reflector to enclose the core, bringing it to the brink of criticality.
And the only thing keeping them apart.
The only thing was a screwdriver. The sources are very clear on this. He was physically holding them apart with a standard flathead screwdriver.
Screwdriver. A
Yep.
simple hand tool was the only thing preventing a nuclear reaction.
Yes. And it slipped. The screwdriver slipped, the hemisphere slammed shut, and the core instantly went critical again. Another massive blue flash of radiation.
But he saved the others in the room.
He did. He instinctively ripped the hemispheres apart with his bare hands, stopping the reaction. It likely saved everyone else's life, but it condemned him.
He absorbed a staggering dose. The sources say around 21 gray. What does that number even mean in terms of survival?
It's an unsurvivable dose. For context, 5 gray is considered fatal, even with the most aggressive modern medical care. So Louis Slatin received 21 gray in a fraction of a second.
It's an instantaneous biological catastrophe.
Completely. He died 9 days later in agony from the most extreme form of acute radiation syndrome.
The Demon Corps is infamous, but these criticality accidents didn't just stop after the war.
Not at all. There's the case of Cecil Kelly, a chemist at Los Alamos who was killed in 1958, a completely separate accident.
What happened with him?
He was working near a large processing tank when a plutonium solution inside it unexpectedly went supercritical. He was standing right next to it.
And his death was maybe the fastest of all.
It was. He received an estimated dose of 39 grays, nearly double what Slotin got. He died just 35 hours later. And it was these terrible, terrible cases that finally forced the implementation of passive, fail-safe controls. Systems that made human error like that impossible.
It's easy to look back at that time, the early 20th century, or the chaos of the Manhattan Project, and just think, well, they didn't have protocols.
Right.
But what happens when the very foundation of modern safety, your protective gear, what happens when that fails completely? And that brings this whole discussion right into the modern era with the tragic case of Karen Wetterhahn.
This is such a sobering story because this happened in 1996 at Dartmouth. Long after safety culture was a global standard.
And Karen Wetterhahn was not an amateur. She was a leading expert on toxic metals. She knew what she was handling was dangerous.
Absolutely. And she followed the protocol. That's what makes this so unsettling. She was working with dimethylmercury, an incredibly potent neurotoxin.
In a fume hood, wearing gloves, doing everything right.
Everything she was taught was right. And then a single drop, just one accidental drop of the chemical, fell onto her latex glove.
Her standard lab glove.
Her standard latex glove. And that tiny detail, that one drop on a common piece of equipment, that's where the whole system failed. She just followed procedure, wiped it off, and thought nothing of it.
Assuming, as anyone would, that the glove protected her.
Exactly. But her death was the horrifying discovery. The sources show that dimethylmercury penetrated that latex glove in seconds. It just wasn't a barrier at all. The toxin went straight through her skin and into her bloodstream.
And it wasn't an immediate thing, which is just so insidious.
No, the symptoms for dimethylmercury poisoning take months to appear as the toxin slowly builds up in the brain. Months later, she started having neurological issues, losing coordination, trouble speaking. She died 10 months after that single drop.
So her death proved that one of the most basic pieces of safety equipment was completely useless against certain compounds.
It sent a shockwave through the entire global chemistry community. It proved that this chemical was far more dangerous, far more insidious than anyone had realized. And her sacrifice led to immediate, mandatory changes in safety protocols.
Like what?
Like the total abandonment of standard latex gloves for these high-risk chemicals and the mandatory use of highly resistant multi-layer laminated gloves. Her death rewrote the safety manual.
These stories are they're startling because they really underscore that the path to knowledge is often paved with this unforeseen, terrible personal sacrifice.
And if you connect all these dots, the central lesson is really clear. These specific cases, they're not just historical tragedies. They're these fundamental reminders that our knowledge of danger often comes after the breakthrough. The risk is just inherent in exploring the unknown.
Right. The final critical takeaway from all these sources is the legacy of that sacrifice. These scientists died because of gaps in our knowledge, and their deaths directly advanced the safety protocols that protect every single researcher today.
Every single one. Every time you see a scientist working safely behind thick shielding or wearing double laminated gloves or using remote manipulators, you are looking at the direct result of the tragic lessons learned from the Curies, from Daly, Slotin, Kelly, and Karen Wetterhahn.
They paid the price so that future generations wouldn't have to.
They paid the ultimate price so that science could finally understand the danger it was unlocking.
Which brings us to a final provocative thought for you, the listener, to think about. We know the dangers of yesterday's science because history teaches us that safety protocols are written in retrospect. So what materials, what advanced research, what cutting-edge physics experiments being pioneered right now might carry an unrecognized long-term personal cost that we'll only discover years or decades from now? The history of discovery suggests that the danger is already out there, just waiting to be revealed.